Well, welcome back to the Algebra 2 jungle, and we got a real treat for you tonight. We're going to take a look at both arithmetic sequences and geometric sequences. Little bit of review from Common Core Algebra 1 here, in that we were exposed to arithmetic sequences, and this was based on what we would have called constant addition in order to generate the next term. An example of what an arithmetic sequence might look like is something like 3, and then 7, and then 11, and then 15, etc., where we're continuously or constantly adding a 4 to each term in order to generate the next term. Another type of sequence was a geometric sequence, and the theme there was that we had what's called constant multiplication. And I'll give you an example of one of those guys. But the key is it's all revolves around multiplication in a geometric sequence. So it might have gone from 2 to 6 to 18 to 54, etc., where we're constantly multiplying by a 3 in order to generate the next term. Well, we're going to jump right into some pretty funky notation here today, and we're going to give you two varieties of notation. So we're looking at an arithmetic sequence, and we're going to define it recursively, okay? And they said if you are given f of 1, which would be we can make a little note here, that's the first term, okay? Then the nth term is generated by f of n minus 1, make sure that's a minus there, okay, plus the letter d. And this guy right here we have a name for him. We call him the previous term. Okay? Or a different set of notation using subscripts is we'd say, okay, if you're given the first term again, then the nth term is generated by the previous term plus d, and we're using some subscripts here. This is a subscript of n, and this is a subscript of n minus 1, and again, this term right here is called the previous term because it's the term that occurs just prior to the nth term. And this letter d is called the common difference. It's the difference between two consecutive terms, and it can be either positive or it can be negative. Okay, and it's basically, this is the amount that we are adding to each term in order to generate the next term. So we threw a lot of jargon at you in that last slide. Now we're going to try to sort it out, dissect it, and kind of put it into action, so to speak. And so here's the key. They're giving me the nth term here, defined recursively, because what you'll notice is the nth term here is dependent upon the previous term, and they said all you got to do is add 10 to the previous term. And they gave me a starting point. And this always has to be given. They will always tell us who the first term is. And so we could say, well, I want the second term. And what I'm going to do is I'm going to substitute a 2 in for each of these n's. And that's going to be f of 2 minus 1 plus a 10. And I'm going to go in slow motion here. So, of course, 2 minus 1 is 1. And who is f of 1? Well, based off of this definition, f of 1 is a 2. So I'm going to say 2 plus 10. Or in other words, I'm going to say f of 2, the second term, is equal to 12. And they wanted the next 3 terms. So I've got 1 done, 2 to go. And we'll see if we can't change colors here a little bit. And let's see. So the third term, f of 3, is going to be defined as f of 3 minus 1 plus 10. Which is really f of 2 plus 10. Who is f of 2? Well, we found out just moments ago that it's a 12. So we're going to say 12 plus 10. Or in other words, the third term in this sequence is really 22. All right, so really, mathematically, it's not that challenging. It's just, I think, developing a sense of comfortability with the notation here today. We want to get one more term. We'll say the fourth term is defined as the 4 minus 1 plus 10, which is really the third term plus 10. We know that the third term is equal to 22. Therefore, the fourth term in this sequence is going to be 32. So just to wrap it all up, our sequence is going to go from 2 to 12 to 22 to 32 dot dot dot. And then from there you could easily generate the next terms 42, then 52, 62, etc., just continuously and constantly keep adding a 10. Well, the question remains the same. They said, can you find the next three terms? And conceptually, this is going to be the exact same as the last slide, but the notation is going to be a little different. And so we're going to use subscripts here. And I think we've got to be fluent with both the function notation we used on the last slide and the subscript notation on this slide. It seems to be 50-50 as to how they might go about this. Notice they already did give me the first term, so I'm going to start with a sub 2, which is a sub 2 minus 1 plus 7. And I'm going to try to be especially careful with my handwriting here. 2 minus 1 turns out to be 1. We know that a sub 1 is defined as negative 2. Therefore, a sub 2 is really 5. Alright, so we've got a sub 2 is equal to 5. Let's see if we can get the third term. That's going to be a subscript 3 minus 1 plus 7, which is a sub 2 plus 7. And we just found out moments ago that a sub 2 is equal to 5. Whoops, that should be a 7 right there. Yeah. Therefore, the third term in this sequence is really 12, or 5 plus 7 is 12. Let's go get one more term before we wrap it up and call it a day here. Let's see, the fourth term is going to be a with a subscript of 3 minus 1 plus 7. And that's going to see a sub 2, the second term, plus 7. And we know the, oh gosh. Let's fix this. Yep, hopefully you were screaming. That should be a 4, which makes this a 3. And the third term we just found out was 12. So therefore, the fourth term in this sequence is going to be a 19. And just to wrap it all up, this sequence is going to start with negative 2 and then continuously add 7. And we'll go dot dot dot. The next term would be 26, and then 33, 40, 47, etc. So notationally speaking, there's two different methods for defining or expressing an arithmetic sequence. And the first one is this recursive one that we've been using so far in the video. But the drawback to a recursive is that it's dependent on the previous term. Okay? And which is great. If you're just looking for like the first three terms, great. You're golden with the recursive. However, the recursive gets really annoying if you were trying to find the 100th term within a sequence. Just imagine how much work that would be, because you can't get the 100th term until you first find the 99th term. And you can't get the 99th term until you find the 98th term. So really you'd have to start at scratch with the first term and go term by term by term until you got to the 100th term. And that's a lot of work. And so we're going to look for shortcuts, because there are a lot of patterns here that we could find. And so instead of defining it recursively, a lot of times we're going to define it explicitly, which is a form that allows us to easily find any term at the drop of a hat, in other words, very quickly. And basically, here's what you want to get in your notebook. It's an expression for the nth term that's not dependent on the previous term. So if you want the 100th term, you can go right from the first term to the 100th term and skip all the terms in between, which is much, much quicker and more efficient. Well, I've got a real interesting bear for you here in this question. We've got here a recursively defined arithmetic sequence, and we know it's arithmetic because of the adding right here that's taking place. And we're basing that off the idea that the first term in this case is equal to a 5. Now, ultimately, we want to try to find the value of the 100th term. But we don't want to find every single term from 1 to 100, because that would take forever and it would be the most boring thing ever. So we're looking for some shortcuts to see if we can find the 100th term without having to find every single term in between 1 and 100. But to get us warmed up, let's see if we can find the second, third, and fourth terms. And we know that the second term is going to be the first term plus 4. And we know the first term's a 5, so 5 plus 4 tells me that the second term is equal to 9. Then the third term is the second term plus 4. In other words, 9 plus 4 gives us 13. And then the fourth term is going to be the third term plus 4. 13 plus 4 gives us 17. So here's what happened. We started with a 5. We added 4 once to get 9. We added it a second time to get 13. And we added it a third time to get 17. And that's going to lead us right into part B here. Okay? Let's see. How many times did you have to add 4 to the 5 in order to get the fourth term? So in order to get the fourth term, we had to add the 4 3 times to the initial term. Okay, we had to add it 3 times to get the 4th term. We would have had to add it 4 times to get the 5th term. We would have had to have added 5 times to get the 6th term, and so on and so on. And hopefully we're jumping on this pattern here. So the question is, how would you get a sub 100? Oh gosh, what did I do here? Okay, I think we're all set. I almost screwed up the screen here. So the question is, how are we going to get a sub 100? Well, what you would do is you would start with the 5, and then you would start adding a 4 to it 99 times. Okay, do you see that? You'd have to add the 4 99 times. So instead of doing all the adding, I'm going to do 99 times 4 and then add that to the 5, and I think that's going to give me 401. Now, last but not least, can we write an explicit formula? And an explicit formula is the opposite of a recursive one for the nth term of this arithmetic sequence. And so here's what I'm thinking. The nth term, okay, is going to be something times the common difference plus the first term. Now, the question is, if you want the nth term, you're going to multiply by n minus 1. And why is that? Well, remember when we did the 100th term? We took the common difference and multiplied it by 99. Okay? If you wanted the 200th term, you'd multiply the common difference by 199. Or simpler, if you just wanted the 15th term, all you got to do is multiply the 14 times your common difference and then add it to the first term, and you've got it. And so this explicit formula allows us to go find any term without worrying about its previous term. Okay, so they want me to write an explicit formula. Again, that's the opposite of a recursive. And just real quick recap, we said it's going to be n minus 1 multiplied by the common difference plus a sub 1. Now, just by looking at this sequence, the very first number is always your a sub 1. So we can put that off to the side. The first term's a 3. And then the question is, what are you adding by every single time? So it looks like you're constantly adding by 7, and we call that the common difference. So the nth term is going to be the quantity n minus 1 multiplied by 7 plus the 3. And a lot of times you will see us distribute the 7. And so I got 7n minus 7 plus 3 combined like terms. And my nth term is going to be 7n minus 4. And this is the explicit formula for this arithmetic sequence. Now the notation's a little bit different here. Just as far as an equivalent form, we could say a sub n is equal to a subscript n minus 1 plus 9. And they're telling us right here that the first term is equal to negative 3. And this 9 right here is the constant that we're adding by. So the common difference is a 9. And once you know the first term and your common difference, you're good to go. And we're going to say the nth term is n minus 1 multiplied by 9. In this case, plus negative 3 or just minus 3. If we distribute the 9 really quick and then try to combine like terms, we're going to get 9n minus 12, and boom, right there's your explicit formula. So we're at about the halfway point of tonight's lesson, and we're going to make a gigantic shift here from talking about arithmetic to now focusing on geometric sequences. And the big change here you're going to see is now we're going to be multiplying by some constant amount instead of adding some constant amount. And our definition, I'm going to give you 2 versions of the definition. First one's going to be in what we call function form. And we're going to say that the nth term recursively is going to be the previous term, catch this, multiplied by r. Instead of adding d, we're multiplying by r. Or if we use subscripts, we could say that the nth term is the previous term times r. Now, who is this rascal we call r? It's called the common ratio. In other words, it's the ratio of 2 consecutive terms. And that r can be positive or he can be negative. And it's often a fraction a lot of times, especially in our course. So here they want us to find the next 3 terms of this geometric sequence that's defined recursively. Again, recursively just means that the value of the nth term is dependent upon the previous term, n minus 1. And I'm going to go pretty slow here, just again to practice the notation and such. And certainly I would encourage you to go as fast as you feel comfortable doing so tomorrow in class. But for starters, they told us the first term, so I'm going to jump right into the second term, and I'm going to substitute a 2 in for each of these n's. And so what I really have is f of 1 multiplied by 3, and they defined f of 1 as 4. So I know that the second term is got to be a 12. Alright, time to change some colors here. And let's see. Now the third term is got to be f of 3 minus 1 multiplied by 3, which is f of 2 times 3. We just found out moments ago that f of 2 is a 12. Therefore, the third term is really 36. And now let's go get that fourth term real quick. The fourth term is going to be defined as f of, substitute that 4, then multiply it by 3. So this is f of 3, aka the third term, multiplied by 3. 36 multiplied by 3. Oh my garage, we're going to try to do this on the spot. 18 carry the 1. I think 108. So the fourth term is going to be 108. And if we put this all together here, the first term was a 4, then we multiplied by 3 to get 12, we multiplied by 3 to get 36, and we multiplied by 3 to get 108, and then you could just continuously multiply by 3. I think the next term would be 324, and then after that I'd have to go to the calculator. Same concept here, we're just looking at some different notation, and we're going to try to throw you another little curveball by practicing multiplying our radicals together, so we're incorporating a little bit of review from earlier in the year at the same time. So the second term is going to be a sub 1, aka 2 minus 1, multiplied by radical 5. So that's going to be 2 radical 5 multiplied by radical 5. And let's see, if we go in slow motion, that would be radical 25, which 2 times 5 is going to give me 10. So the second term is 10. And let's go see if we could find the, whoa, where'd that line come from? Alright, we'll get this cleaned up here. The third term is going to be a sub 2 multiplied by radical 5, which we know that that's a 10 times radical 5. And this one's not as bad. It's just we're gonna literally just call it 10 radical 5. And then the fourth term might be a little more interesting. The third term multiplied by radical 5. Let's see, that's 10 radical 5 times radical 5, or in other words, so that's 10 radical 25, or also known as 10 times 5 for a 50. So far, the two geometric problems we've done so far were defined recursively, and we're thinking, okay, recursive is great, it's good stuff, but man, does it make it really hard to find big terms like the 100th term or the 1000th term and things like that. So we're going to try to work on converting from recursive to an explicit form. And to get you warmed up, we're just going to try to find the value of a sub 4. And I'm going to go, we already know that a sub 1 is defined as a 2. A sub 2 is going to be 2 times 5. A sub 3 is going to be 10 times 5. And then a sub 4 would be 50 times 5 for 250. And so on and so on. But what you'll notice with here, starting with the first term, you multiplied by 5 once to get 10, multiplied by a second time to get 50, and we multiplied by a third time to get 250, thus leading us into the next question. How many times did you really need to multiply the 2 by 5 in order to get the fourth term? In order to get the fourth term, what we did is we multiplied the first term by 5 just 3 times. Multiplied it by 5 3 different times to get the fourth term. So this number here is always going to be 1 less than this number right here. If you want the 50th term, just multiply by 5 49 times. Alright, so can you find a sub 10? Well, that would be the first term multiplied by 5 9 times. Okay, dot, 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 multiplied by 5, and there'd be 9 of those 5s in there. And we're thinking, well, instead of doing it that way, let's see, we've got repeated multiplication here, so let's multiply by 5 raised to the 9th power, and by golly, that's going to be some big number. I got like 3,906,250. I guess that was 3 million. I might have said billion there. But anyway, real big number. So a nice shortcut where we're able to find the 10th term without having to waste our time finding the 5th, 6th, 7th, 8th, and 9th terms before we did it. Okay, now as far as writing a formula for the nth term of a geometric sequence, we're thinking the nth term is always going to be the first term, who is then multiplied by the common ratio raised to the n minus 1 power. And so when we found the 10th term, we just multiplied by r raised to the 9th. If we want the 50th term, our exponent would be a 49. If you want the 100th term, the exponent is going to be 99. In other words, the exponent should always be one less number than the nth term. So we're coming down the home stretch here. Right off the bat, we could recognize this as a geometric sequence because it looks like we're continuously or constantly multiplying by 6 to get the next term. Multiply by 6, yep, get the next term, and on and on. And we want to try to write an explicit formula, which again is the opposite of a recursive one. And so if we just write down our formula, and then we'll plug in the numbers that we know, we can, just by observing the sequence, we know that 1's the first term. The common ratio is a 6, so let's plug a 6 in there. And bada bing, bada boom, you are done. You don't need to do anything else to that term. Real similar idea here. We're looking for an explicit formula, and this guy right here is the same thing as saying the nth term is the previous term multiplied by 10. So this 10 right here, that's going to be your common ratio, and they told us right here who our first term was. So again, I'm just going to copy down my formula and take my time, make sure I don't screw anything up. And so the nth term is the first term, 0.5 or 1/2, with a common ratio raised to the n minus 1 power. And again, there's no cleanup on this one. We're just going to leave it as is and say this is an explicit formula for the nth term of our geometric sequence.